So Srividya, I'm just formally introducing the speaker, okay?
Yeah, please start. I have started the recording. Yeah, please.
So, good evening, Professor Federico Rosei, and very good morning to all my colleagues and students at Indian Institute of Science. On behalf of IQTI, I welcome you to this ISC Quantum Technology Initiative Breakfast Talk by Professor Federico Rosei. His current affiliation is Center for Energy Materials and Telecommunications, Institute National Dealer Researches Scientific Variance, Canada, where he was also served as director from 2011 to 2019. He held the Canada Research Chair in Nanostructured Organic and Inorganic Materials during 2003-2013. And since May 2016, he was the Canada Research Chair Senior in Nanostructured Materials. He has received several awards and honors, including Frederick Wilhelm Bessel Award from Alexander von Humboldt Foundation in 2011. IEEE NTC Distinguished Lectureship Award 2015-2016, Changjiang Scholar Award China, and several other awards, including IEEE Photonics Society Distinguished Lectureship Award 2020-2022, Guangxi Golden Silk Ball Friendship Award, and TMS Brima Combe Medal in 2021, and very recently Woodson Fellowship from Royal Society UK. With this brief introduction, I would now request Professor Federico Rosei to deliver his lecture on this virtual platform on multifunctional materials for emerging technologies. Now this online flows is yours.
Okay, thank you so much, Professor Basu, and thanks to everybody, the organizers, for giving me the opportunity to share some of my work with you this morning. I believe it's 8:30 in the morning in India, so the time is not ideal for you guys. It's I guess I'm very grateful that you woke up so early to listen to my lecture. Well, despite the inconveniences of being in the middle of a pandemic, I guess we can be grateful for modern technology that allows us to connect across geographical boundaries and time zones, even when we're essentially unable to travel these days. Okay, so I will go in presentation mode. And essentially, I'll start by briefly introducing a little bit my research program. So my training originally was in physics, studying properties of surfaces and interfaces. And over time, I evolved into, shall we say, a material scientist, looking more and more at properties of different classes of materials. We look at fundamental aspects. The top image shows self-assembled systems and two-dimensional polymers. And then we transition towards many different types of applications, studying, for example, biomedical materials such as biocompatibility and antimicrobial coatings on one hand, which is some work that conceptually links me a little bit with Professor Basu. And then we also work on organic electronics such as thin film transistors and sensors, organic light emitting transistors, aerospace materials such as self-healing materials and fiber optics. And of course, the main topic for today are renewable energy technologies. Most of our work in this space these days focuses on solar technologies, looking at third generation photovoltaics, hydrogen generation, and so-called solar windows, although we also look at solid state lighting and energy storage. I won't really have time to go into detail into those other topics. I just wanted to mention it. So, Of course, you will have the impression that our work is scattered in many different directions, and there is some truth in this, but nevertheless, there is also a fundamental guiding principle that sort of assists us in our research, and essentially it consists in looking at structure property relationships in materials. We want to understand the role of morphology and composition and how they determine the functionalities of materials, and then looking at how these materials can be used as building blocks for different types of emerging technologies. And by optimizing structure property relationships, we can then optimize as well device performance. We mostly look at nanoscale materials, and that's why we focus on surfaces and interfaces, because in a nanoscale system, there's very little volume and most atoms reside at the surface. So, as mentioned, we look at different classes of materials. The sort of, broadly speaking, the main focus of today's presentation are multifunctional materials. I guess, you know, we have limited time. I'm sure you have a busy day ahead, and I hopefully have a restful night once I finish this presentation with you guys. So I will give you a snapshot of what we do in the space of multifunctional materials. As the name suggests, these are materials that exhibit two or more functions. But so even while a lot of our work is fairly fundamental, as mentioned, we've transitioned towards different areas of application. And when we think of applications, we focus on sustainability. There is a fundamental question here whether sustainable development is even possible. To some extent, I believe that sustainable development in a way is a contradiction in terms, or an oxymoron. But having said that, the United Nations have identified the so-called 17 Sustainable Development Goals, which I list here. In reality, I believe that we could reduce to a smaller number, but anyway, these are the grand challenges that have been identified by the United Nations as priorities to be addressed for a long-term peaceful coexistence of all living species on the planet. And so they're listed here, and I underlined the ones that I believe as academics we are able to contribute. In particular, number 3, good health and well-being. Number 4, quality education, of course. Number 6, clean water and sanitation. And number 7, affordable and clean energy. Number 11, sustainable cities and communities. Number 12, responsible consumption and production. And number 13, climate action. So especially in my case, as an academic, as a material scientist, I believe that our research and our efforts in training new generations of scientists and engineers can have a certain impact on these specific grand challenges. Now, okay. As mentioned, I want to focus in particular on the energy challenge. I believe this is, if I had to pick one main challenge that we urgently need to address, it's the energy challenge. You might be surprised maybe because we're in the middle of a pandemic, and that's understandable. Health is and will always be a major challenge for humanity, but humanity has survived many pandemics in history, and they tend to last a few years. This one is not going to be different. It's tough while we're going through it, but we will go through it. We will prevail. It's just a matter of time and of getting organized. And on the other hand, the energy challenge is something that if we don't address it really quickly and urgently, this can essentially, in my opinion, make us crash and burn. So these two graphs are borrowed from an article published in Physics Today about 14 years ago. And yet, they're still very accurate. So on the left, you see a breakdown of the energy sources. that we use on a global scale. And as I mentioned, even in 2021, it's remarkably accurate. About 80 to 85% of the energy we use is based on fossil fuels. A small percentage, maybe 4 or 5%, is nuclear. A couple of percent is hydroelectric. And everything else here is sort of generically labeled as biomass and other, but these are essentially the renewable energy technologies, which means these encompass, besides biomass, also solar technologies, geothermal, wind power, tidal energy, and so on. So our challenge is clear. We have to replace about 80 to 85% of fossil fuels because we know that on one hand, they're non-renewable, at least not on a time scale that matters to us. And at the same time, they're also highly polluting. They cause substantial CO2 emissions, which in turn are causing climate change. But if we were to sort of come up with a model for sustainability, and if we were to think about all the variables and all the sort of issues around sustainability, I think we have to draw some conclusions, some very difficult and not very popular conclusions from the graph that is depicted on the right side of the slide, which shows world population as a function of time. Let's go back in history a few hundred years, and we find that human population was much smaller than what it is today. For many years, human population was growing very slowly, and it didn't reach 1 billion people until essentially the 1800s. You guys are based in India, so this must make you laugh because the population of India today is more than 1 billion people. So your country has more people today than all the world had about a couple of hundred years ago. Can you believe that? This is quite amazing, but it gives you an idea of how fast population has been growing since roughly the 1800s, as you can see from the graph, going from about 1 billion back then to almost 8 billion today. Now, the 1800s is the era that we refer to usually as the Industrial Revolution. But we know that the Industrial Revolution was powered by coal. Now, coal is the first fossil fuel that humanity used on a large scale. And after coal, we started using natural gas and oil. And there's many bad things that can be said about these fossil fuels. Of course, I already mentioned them. They're not renewable and they're highly polluting, but they do have some advantages. And in particular, they were for a long time, and to some extent they still are, low cost. And they also have a very high energy density. So the availability of these new sources of energy, these fuels, essentially prompted the development of many technologies, including, of course, information communication technologies that we're using today to connect across thousands of kilometers of geographical distance. If the pandemic were not here, maybe I would be in India in person. I would have traveled using flights that would have taken me there, which again was not possible a couple of hundred years ago, but was made possible by the energy density of fossil fuels. And in turn, this also yielded many medical advances and all sorts of other advances, so that, especially in rich countries, the average lifespan of humans has increased greatly, especially in the last few generations. In countries like Canada or Italy, where I'm originally from, the average lifespan is over 80. And this was not true just a few generations ago. And of course, it contributes to this population boom. Now, why is this population boom something I focus on so much? I mean, look at it here. World population increases at a rate of 200,000 people per day. That means 70 million people per year. That's roughly twice the population of Canada. And it also means that in 15 years, you have 1 billion extra people on the planet. So in less than one generation, there's 1 billion extra people. And guess what? More people need more energy, they want more food, they need more clean water, they also want good health services, they produce more waste, they need jobs. Essentially, more people will affect all the sustainable development goals, all of them. And so this is one aspect that we need to be concerned about, although as scientists, you can appreciate that there's nothing we can do about it because world population is not something we scientists can control or even suggest how to control. This is a sociological aspect, economic, political, you name it, but it's not something that we scientists can address. I just wanted to point out that as long as population grows exponentially, there will not be any scientific or technological solution to the energy challenge or to most of the sustainable development goals for that matter. Now there's another aspect that I want to emphasize, and you can see it here. This is the Earth at night from a satellite. So there's a collection of images taken from satellites and patched together. And of course, this picture is fascinating, and it also tells us a lot about the condition of humans on this planet. On one hand, we are wasting a lot of energy, of course, and on the other hand, the availability of energy is not the same for everybody. Now, if you look at Australia, most of it is dark, but then again, you recall that Australia is essentially a huge desert with people living mostly around the coast. That's where you find patches of light in this image. And so Australians, the 20-something million that live there, they're fine. Middle of South America also is dark. Again, I guess there's not that many people living there. That's the Amazon forest. So, you know, you don't expect high population densities, large cities there or anything. But look, on the other hand, at most of Africa, large parts of Central Asia, they're all dark. What does this mean? Well, essentially, the people living in these parts of the world, they don't have any energy. They don't have any lighting at night. When the sun sets, typically around 6 or 7 p.m. or something like that, everything goes dark. The most fortunate among these people may have kerosene lamps, which obviously are not very healthy, and everybody else will essentially not have any light. And if you're wondering how many people live in these conditions, well, there's not an exact estimate, but it's around 1.5 billion people. It's essentially close to 20% of all human population. They don't have access to energy. And you can imagine that these same people also don't have access to well, clean sanitation. They often don't have clean water. They might not have sufficient food, and so on and so forth. So from what I've mentioned here, you can appreciate that what we're looking at is not simply a scientific and technological challenge. I mentioned this already. There's some aspects of it that are sociological and economic and political. And so I've been trying to address this whole situation in a sort of broader and slightly different way than what I would do for a sort of more traditional scientific problem. So I've looked at UNESCO, which is one of the United Nations agencies. This is a United Nations educational, scientific, and cultural organization. And UNESCO has a program that promotes international inter-university cooperation and networking, and this is called UNESCO Chairs. So UNESCO Chair is essentially a network of participating organizations that will work jointly on priority areas of UNESCO, such as education and one or more of the Sustainable Development Goals. And they do this by pooling resources to address these challenges and exchanging knowledge and developing new knowledge. And the idea is that these networks and chairs are supposed to act as think tanks and bridge builders between academia, local communities, research, and policymaking. And in fact, in the best case scenarios, a UNESCO chair can actually inform policy decisions. And this is what we're hoping for, because if there's going to be an impact in the energy space, it cannot be just from new discoveries and innovation. There has to be an intervention of policy. So our UNESCO chair focuses on renewable energy, or if you like, on the grand challenge of obtaining access to sustainable energy for all. And this is done through research built on sharing knowledge in emerging energy technologies. We have over 30 partner organizations in about 20 countries in the South. In the UNESCO definition, South means essentially developing countries, knowing, of course, appreciating that among so-called developing countries, there's different tiers from the very underdeveloped countries, the poorest ones, all the way to countries that are essentially quite developed, including, for example, China and India. So we have programs of visiting professorships and student exchanges. We organize international workshops and seminars. These days, of course, they are webinars, like the one that we're doing right now. And we also train a certain number of PhD students through our PhD Excellence Scholarship Program. And we do this in collaboration with our partners in the South. Now, what kind of research focus is there within this chair? So we look at materials for energy conversion, mostly looking at solar technologies. So the idea here is to develop materials that can absorb as many photons as possible from the distribution intensity that comes to our planet from the sun and transform them into another usable form of energy. So this is the challenge we're looking at. And of course, we want to do this with materials that are low cost, that have long-term stability, and hopefully that are also low energy intensive. We also look at materials for energy saving because, of course, if we're going to address the energy challenge, one way to sort of alleviate the urgency is to buy time by saving energy. And so here you see a brief history of lighting showing how until recently we also were essentially burning oil and kerosene and so on, and then about 100-something years ago we moved to the incandescence filament, which of course was already much better than kerosene lamps, but it's still a highly polluting and inefficient technology. So we're now in the era of solid state lighting, and these LEDs are of course exceptional light emitting devices because they save a lot of money and energy, and they also reduce substantially carbon emissions. And then materials for energy storage. So this is a view graph which is a little bit outdated, so the figures are not really accurate anymore, but essentially it tells us what kind of challenge we're facing if we want to electrify transport. We need to significantly improve the energy density of batteries, because on one hand the driving distance of one charge is usually not competitive with one tank of gasoline, and even now that in some cases batteries can be competitive, they're still pretty slow at recharging, and so that is still a huge inconvenience because you know, you can fill your tank with gas in about a few minutes, but on the other hand, if you have to wait 1 or more hours to recharge your battery, then it's inconvenient to drive long distances. So back to us and back to this map of the world at night from a satellite, and the next sort of picture is what I call a map of possibilities, because you see now that the same areas that are dark at night are the ones that have most sunshine during the day. And so essentially the opportunity here would be to deploy solar technologies in these parts of the world, the same parts that don't really have access to energy. They have so much sunshine, which means that we could really harness the power of the sun. We would have to combine it with efficient storage solutions, as I just mentioned. And I want to emphasize that actually, you know, the slide I showed on materials for energy storage focuses on the electrification of transports, but in reality, we should be mindful of the fact that storage is the common challenge for all renewable energy technologies because they're all intermittent. So this is clear in the case of the sun because it shines during the day and there's nothing at night. And even during the day, whenever a cloud passes overhead, your power can drop substantially. And so this makes the source very intermittent. Other renewable energies are also intermittent. For example, tidal power, of course, depends on the relative distance of the Earth to the moon. And wind power goes in cycles of about half an hour and so on and so forth. So storage is really the key common challenge and one of the big bottlenecks for the sort of large-scale deployment of renewable energy technologies. Now, as mentioned, we're looking at various materials that can harness the power of the sun and convert the radiation of the solar radiation into other forms of energy. And so here we draw inspiration from the process called photosynthesis, used by plants to convert solar energy into chemical energy, which is then stored into the plant. And the prototype technology here was invented by Michael Gretzel about 30 years ago, and these are dye-sensitized solar cells that essentially mimic the photosynthesis reaction in plants. Now, the major challenges that have not really been addressed despite 3 decades of research are the efficiency of power conversion, which is, the world record is about 14%, and the stability, which is also not very long, especially compared to silicon solar panels, which are now certified to last 30 years. So that's pretty tough to compete with. It's not easy to sort of displace silicon solar cells with something else. On the other hand, this concept of dye-sensitized solar cells has 2 big advantages. One is the low cost, and also they're low energy intensive. You might be wondering why replace silicon solar panels if they're so efficient, about 20%, that's quite good, and they last 30 years. And that's a very good question, but see, the part of the problem is that to fabricate silicon solar panels, you actually need a large energy budget. So this means that you cannot fabricate them in any part of the world. In fact, in parts of the world where there is no energy to begin with, you wouldn't be able to fabricate them. But also it means that while you fabricate them, since the energy input is high, and since most of our energy now derives from fossil fuels, then you're going to emit a substantial amount of carbon emissions during the fabrication of silicon solar panels. On the other hand, when you're looking at these alternative 3rd generation solar technologies, then they're low energy intensive. They can be sort of synthesized, fabricated in a chemistry lab with a very low energy budget. So how does this dye-sensitized solar cell work? Well, essentially you have a photoanode, which is the sort of the part of the cell that sort of captures solar radiation. This is made of a mesoporous material, typically a metal oxide like titanium dioxide or tin oxide or zinc oxide. This is usually a wide bandgap semiconductor. And typically these oxides have certain advantages, like they're not toxic, they're very stable, and so on and so forth. Unfortunately, the fact that their large bandgap limits their ability to absorb solar photons, because any material can only absorb photons that have energy higher than its bandgap. And if the bandgap is large, it means that you're only absorbing in the ultraviolet region of the solar spectrum. And if you look at the distribution intensity of the solar spectrum, there's only about 4 or 5% of photons in that region of the spectrum. So that's a huge loss in terms of giving up 95% of usable photons just because your bandgap is so large. So the idea of Gretzel was to sensitize these mesoporous materials using dye molecules that are large organic molecules that absorb in the visible to infrared or even near infrared part of the spectrum. Now, what we and many others have been doing is to replace those dye molecules with quantum dots. What is a quantum dot? It's a semiconductor nanocrystal in which the optoelectronic properties, including, of course, the electronic band structure and the band gap and so on, can be tuned by varying the size, shape, and composition. And so using these as sensitizers, you can again sort of broaden the absorption spectrum of your photoanode, even if the starting point is a metal oxide with large band gap. And these can also be fairly low cost, and at the same time, they're low energy intensive because they can be fabricated in a chemistry lab using wet chemistry approaches. And they're much easier to make than dye molecules that I mentioned earlier. So the idea is that we're going to sensitize those metal oxides with quantum dots to extend the working range, or the absorption range, if you like, into the visible, or even into the infrared or near infrared. And at the same time, you want to maintain good stability and low cost. You can see here the sort of absorption range of various materials that can be used for these quantum dots. The synthesis of colloidal quantum dots, as mentioned, is done through a wet chemistry approach using metal organic precursors. Not very high thermal budget, not very high energy budget in general. There's various sort of steps into any of these processes, but they're all fairly low cost and low energy intensive. And we've mainly focused on giant core shell quantum dots. So we've synthesized whole libraries of quantum dots in which essentially we're looking at a core of one semiconducting material, which is then coated with a shell of a different material. And the reason we do this is that, again, we're looking at structure property relationships, and by using different materials for core and shell, and also sort of varying the relative core and shell size and the composition, the interface, and so on, we can fine-tune the optoelectronic properties. So we've worked on three categories of quantum dot solar technologies. The first one, which I'm afraid I will not be able to discuss today due to limited time, but these are sort of quantum dot solar cells. The world record currently sits at 16.6% of power conversion efficiency, and it's held by the group of Lian Zhuang in Brisbane at the University of Queensland in Australia. So it's a pretty decent world record. It has surpassed dye sensitized solar cells. The other two technologies are quantum dot photoelectrochemical solar cells for hydrogen production, and solar windows made with quantum dot chromophores. And these are the two that I want to share with you today, a little bit of our work in this space. So, hydrogen. Hydrogen is a fantastic fuel because when you combust hydrogen in a fuel cell, your only byproduct is water. So environmentally, it's fantastic. Now, there's three challenges in sort of deploying a hydrogen economy. One is production of hydrogen. How can you extract it? See, in the atmosphere, only about 1% of the composition of the atmosphere of our planet is made of hydrogen. So extracting it, sort of grabbing it from air, is not very efficient. And in any other case, hydrogen is bound to other elements, other molecules. Of course, as you can imagine, most hydrogen is bound to water, and ideally we want to extract hydrogen from water because about 2/3 of the Earth's surface are covered in water. So this is the holy grail. Right now, and many of you are probably not aware of this, the hydrogen that is used in fuel cells is actually extracted from fossil fuels, mostly from natural gas, which is CH4. And well, again, it's a non-renewable feedstock, so it's and to some extent extracting it from CH4 also causes carbon emission, so this is not a good way to access hydrogen. On the other hand, breaking up water molecules is an exothermal reaction. This means that you need more energy to break up that molecule than what you get back when you combust hydrogen in your fuel cell. And so you need some kind of free energy, so to speak, that will enable you to sort of bridge that gap, that sort of issue of the exothermal reaction. And so the freebie, so-called, is the energy from the sun. The other two challenges related to hydrogen, we don't really work that much on them. We worked a little bit on storage, a little bit on combusting hydrogen. So storage is because H2 is the smallest molecule on Earth, and so storing it in large quantities is difficult. Ideally, you have to liquefy it so that you can sort of condense it into smaller volumes, but liquefying hydrogen, of course, requires energy. So this is one big issue. And the other one, of course, is the efficiency of combustion in a fuel cell, mostly because the typical catalyst that is used for combusting hydrogen is made with platinum, which is at the same time rare and expensive. And so there's substantial research that is going into replacing platinum with other catalysts that are that have similar sort of activity and ideally long-term stability, and that are less rare and expensive. So these are the major processes that are involved in photoelectrochemical water splitting. So the first process is your photoanode will absorb light. It's a semiconductor and it absorbs any photon that has energy higher than the band gap. The absorbed light will create an excited state called exciton, and the exciton will then split into an electron-hole pair, and these two charges are then transported across the photoelectrode, and then these charges will reach the surface and they will induce redox reactions so that they will split water into hydrogen and oxygen. What are the requirements for the photoanode? Well, we know that the energy required to split a water molecule is 1.23 eV, which means that the minimum theoretical band gap for water splitting would be exactly 1.23 eV. However, there's a number of thermodynamic energy losses, and there's also an overpotential for the surface reaction to occur. So in reality, the minimum band gap should be about 1.8 eV. We also have to consider other aspects such as efficient charge carrier separation and transport in the semiconductor. You also want strong catalytic activity and stability, and you want these materials to be low cost and made with earth abundant elements. So a very typical sort of main material for your photoanode, again, is titanium dioxide, as I mentioned. In the anatase phase, it has a band gap of 3.2 eV, again, fairly large, only absorbs in the UV. Advantages include that it's inert and resistant to corrosion, it's non-toxic, it reacts under mild operating conditions, and it has a high oxidative power. So your titanium dioxide then will be sensitized with these quantum dots, in our case, giant quantum dots, which have certain advantages over regular quantum dots. So they're more stable and less sensitive to the surrounding chemical conditions. And the band alignment between the quantum dots and the TiO2 is tunable, and it can be tuned in particular by varying the core size and shell thickness. On the other hand, because of the core shell structure, the absorption range is still somewhat limited, and the fact that there is a thick shell can actually affect the efficiency of charge transfer. So this is the working principle. I guess we've already been through it, sort of, but anyway, The exciton is photogenerated, and it dissociates at the quantum dot oxide interface. Electrons are injected into TiO2. They're transported within the titanium dioxide mesoporous film and collected at the front electrode, and then transferred to the platinum counter electrode where hydrogen generation takes place. There's also an electrolyte for transporting holes. Here we also use hole scavengers such as sodium sulfide and sodium sulfite, and these provide shuttle transport for the photogenerated holes. And we've obtained, using these quantum dot sensitized photoanodes, very high values of photocurrent density of 10 milliamps per square centimeter, and to a certain extent we've also obtained fairly long-term stability. You can see here our record values are actually about 11 milliamps per square centimeter, which yield 110 milliliters per square centimeter per day of hydrogen. This is using quantum dots in which the core is lead sulfide and the shell is cadmium sulfide. Now you see here there's another problem that you can probably already notice. Lead and cadmium are heavy metals and they're toxic, and so at some point, even though we obtained very good results for this type of material, we also started developing in parallel greener processes and greener materials that are non-toxic, or anyway less toxic. And so here you see we worked on colloidal giant core shell quantum dots that are free of heavy metals. There's no heavy metals, and that absorb in the near infrared. These are made of copper indium selenide and copper indium sulfide. Again, the sort of reactions are wet chemistry approaches, fairly, low cost, low energy intensive, and so fairly straightforward. In here, of course, there is a trade-off. So the best photocurrent density in this case is about 3.1 milliamps per square centimeter, which means we lose a factor of almost 4 compared to lead sulfide, cadmium sulfide core shell quantum dots. So this is an issue to be addressed. We made these materials which are more eco-friendly, but the trade-off consists in a substantial loss in performance. Now, the last technology I wanted to share with you are so-called luminescent solar concentrators. I prefer to call them solar windows. Here, essentially, the idea is to use the surface of windows, especially in tall, large buildings, to use the surface of windows to power part of the building's energy needs. So you don't want to cover your windows with traditional solar cells like silicon solar panels, because these are not transparent. And so basically your trade-off would be huge, because you would give up completely on illumination during the day. So you need a different concept. And so what you do is you encapsulate a polymer waveguide, and this polymer is essentially transparent to solar radiation. So it's encapsulated in glass. You place it in front of your window. It lets through most of solar light, so you don't really lose in illumination. Now you're at the sides of this encapsulated polymer, as if it were as if you're framing a picture. That's where you place silicon solar cells, which are therefore thin and long, and they frame the whole encapsulated polymer. Now within the polymer, you're going to embed a certain number of chromophores. In our case, these chromophores are quantum dots. And what are chromophores? Well, they act like antennas, and so essentially they absorb incident radiation at one wavelength, and they re-emit it at a different wavelength. And the re-emitted photon will travel through the waveguide until it hits one of the solar cells that frame it at the edges. And so you've then converted part of your incoming light into electrical power. If you want to make this this technology efficient, then your antennas or chromophores need to have a large Stokes shift, which means a large difference between absorbed photon and re-emitted photon. Because if your re-emitted photon has a wavelength similar to the absorbed one, then it might easily be reabsorbed by another chromophore, and then it would count as a loss. It would be sort of lost from power generation. So this is one of the aspects. And again, you can, to a large extent, engineer the Stokes shift by varying the core shell and thickness and so on. And so initially, also in this case, we worked with lead sulfide core, cadmium sulfide shell, and we obtained our best values once again using this material, making solar windows in which the quantum dots have a large Stokes shift and have high optical efficiency and so on. Also in this case, we moved from this concept of toxic materials towards greener processes and materials. And so our latest generation of dots are actually carbon dots. So they're mostly made of carbon. There's a little bit of oxygen, hydrogen, and nitrogen. In fact, you'll notice these are the 4 most abundant elements on the planet. So in terms of sustainability of these materials, it couldn't get any better. And these carbon dots are reasonably efficient. Of course, they're still a trade-off, but they're quite efficient, and they're obviously much more eco-friendly as opposed to the lead sulfide, cadmium sulfide quantum dots. Now, I also wanted to share with you a sort of small side project that we've been working on in parallel to all this. This isn't really related so much to energy, and it may have more applications in biomedical technologies, but it's a pretty nifty concept, and it's due again to the structure property relationships of these quantum dots. Now, suppose that you want to measure temperature in a nanoscale system. As you can imagine, you can't do it through mechanical contact like you would do with a regular thermometer based on mercury, because you wouldn't really have efficient contact, and so your temperature measurement would not be accurate at all. So one way to do it is optically using nanoscale thermometers, which are made with quantum dots. What we noticed in our case, in our giant quantum dots, is that we were focusing on their absorption properties, but they also have emission properties. And in fact, we noticed that these systems exhibit a double photoluminescence emission. And in particular, the intensity ratio of the 2 photoluminescence peaks varies linearly with temperature in a large temperature range. And so this makes these quantum dots an efficient optical nanothermometer, which can allow us to measure temperature in a nanoscale system with high sensitivity generation systems such as quantum dot solar cells, as well as hydrogen generation using photoelectrochemical solar cells, and also luminescent solar concentrators or solar windows, which use quantum dots as the chromophores or antennas. I'd like to mention that I'm one of the associate editors of Journal Materials Chemistry C. Now, in 2013, Journal Materials Chemistry split into 3 new journals, A, B, and C. And C deals with anything related to optical, magnetic, and electronic properties of materials, such as display technologies, sensors, printing, optics, electronics, magnetism, and so on. So I encourage you to submit to our journal. Actually, we recently got the latest metrics. Our impact factor for 2020 is about 7.3, so it keeps increasing. Our rejection rate is also pretty high, about 80%. So want to make sure you're aware that it's not easy to publish in JMCC. If anybody is interested in writing a review article, I'll be happy to discuss potential topics and see if we can commission it. And I owe a debt of gratitude to the funding agencies that support us, from both the provincial government of Quebec as well as the federal government of Canada. And also I want to acknowledge over 20, maybe even more than 25 Canadian R&D companies that we've worked with over the years, that we've partnered with and jointly collaborated on high-tech projects and so on. And as much as we don't know when the pandemic will end, we're pretty sure that at some point it will be behind us. And when that is the case, I hope I will have the opportunity to visit India again. I've already been there 3 times, and I'd certainly like to come back. And at the same time, you are also welcome to visit us here in Canada. If you visit us, of course, you should be aware that our winter is pretty harsh and our summer can be pretty hot. So right now we've had a hot spell, and during which almost every day it's more than 30 degrees. Might be not so much for you guys, but I can assure you that it's quite unusual here. So we're living the effects of climate change and global warming. And so during the summer, if you visit us during this season, you can share your work, your kind of research interests and results, and you can also participate in one of our traditional water fights, of which you see a picture here. So this is one of our traditions during the summer, to organize one of these events, sort of extracurricular activities. And thank you very much for your attention.
Right. Thanks, Federico. I think the summer seems very enticing in Canada, frankly. Okay. Do we have questions for Federico? Please just use the raise hand button, and then I will just call on you to ask a question. So maybe I can ask us to start. So Federico, you were talking about these solar windows, right? These luminescent solar concentrators. So what is the sort of the state of the technology right now in this field, in LSCs? Like, are these being commercially employed, or is this still?
Yeah, that's a very good question. No, we're not quite there yet. There's a lot of technological hurdles, and part of the issue is the fact that you're absorbing in one wavelength and re-emitting at a different one, so you're not using the framed solar cells at their best efficiency. So you're using the fact that in a large tall building you have many windows. So potentially you can exploit this aspect, but on the other hand, the concentration is not that efficient. The solar cells do not work at their best, so it's not commercial quite yet. I guess there's a lot of efforts going into this because, in particular, high rises are more and more common, especially in large cities, of course, and if you want to power them with solar energy, you can't really rely on placing solar cells on the roof. That's not very efficient, and so this concept has a lot of potential, but it's not definitely not commercial yet. Okay, because so I've always been fascinated by using solar windows because I see a lot of windows and I see a lot of sunlight. So I've been thinking about this problem actually, and are people exploring the idea that rather than using a dense non-transmissive solar cell, maybe you can use a
10% efficiency, sorry, a 10% absorption solar cell, very low density absorber, and use that as a window. Is that something that you've explored or?
We haven't explored this, but there are other studies which essentially develop a concept similar to what you said. So that is a concept that is being explored by others. I haven't really done a comparative study of what we're doing with respect to that case, but it is certainly one potential technological solution to solar windows.
Okay.
Yep.
Okay. Thanks. Thanks. Apurva, you have a question? Please go ahead.
Hello. Yeah. Hello. Yeah. Most of the, well, may not be most, but a significant part of the solar energy is in the infrared, which is below the band gap. So, is there any process which can accumulate energy of several photons before trying to split water with the accumulated energy? This is what happens in, for example, in natural photosynthesis, where some 4 to 5 photons are absorbed first, and the combined energy is used to split water. So, is there any analog of this process which this solar cells that you are developing uses?
I haven't seen it, and I mean it's a very interesting idea, and the concept would be quite nifty. I wouldn't know how to go about it. I mean, you're right, to some extent that's how photosynthesis operates, but unfortunately so far we're only looking at absorbing photons with energy higher than the band gap. So right now device concepts are limited by this aspect, and we essentially lose or give up on all those near infrared photons, because for water splitting purposes we need that 1.8 eV band gap. So this would be a very nifty concept. I just can't think of a way to sort of develop it in a material. But thanks for the idea. I mean, I'm certainly going to think about it. I don't know if it can actually be done, but it's worth thinking about.
Okay, Yogendra, please go ahead with your question.
Thank you. Am I audible to Professor Federico? Am I audible, Professor Federico?
Yes, I can hear you.
Thank you very much for a very enlightening talk, leading the next generation of engineering. I'm a mechanical engineering myself, and congratulate you for some of the exotic options that you have presented for us to generate energy, if not on a large scale, at least scale that might be useful for a human being. That connection, I was wondering, what do you think is the break-even current density that would make it economically viable? For example, we could take your dots and put them on goggles or helmets and so on to charge our cell phones and so on. So I was just wondering whether right now you have achieved about 11 milliamps per square centimeter, whether that is adequate for economic application, or you think you still have a long way to go in that direction?
Well, thank you. That's an interesting question. In most cases, we and others tend to refer to the sort of current density that we obtain in these photoelectrochemical solar cells, but in reality, a more accurate measure of efficiency is the solar to hydrogen conversion efficiency. And so I've given that value of 110 milliliters per square centimeter per day, which is not bad, but in general, solar to hydrogen conversion efficiencies are pretty low across the spectrum of devices that have been reported, both for us and for anybody else working in this field. And usually the target for commercialization would be solar to hydrogen conversion efficiency of about 5%, and currently best values are fractions of a percent. So in essence, to answer your question, we're very far from anything that can be commercial. We need some kind of, both for solar windows and for hydrogen production, we need some kind of breakthrough, and we're not there yet. So in a sense, quantum dot solar cells, where the world record is 16.6%, they're to a large extent closer to commercialization, because that kind of conversion efficiency is quite high. In that case, it's more a matter of improving stability. But for hydrogen generation, no, we're quite far in relation to values that would be considered good enough for commercial purposes.
Thank you for your very candid response to my question. I was just wondering, whether you are in a position at this point to take a patent in some of these, successes that you have mentioned, or is still some way out, some way off, from there.
So sorry, can you repeat the last couple
of
sentences?
Have you already filed a patent or two on some of these exotic options, or you think it's still somewhere down the road?
If we filed a patent, is that the question?
Yes. Have you already filed a patent on these things?
That is the question. Yes.
Okay, so we filed a patent on certain quantum dots for use in luminescent solar concentrators. Okay. That patent is still pending. Okay. We didn't file a patent for hydrogen production. There's two things that I want to mention here. One is that patenting anything related to quantum dots is not easy, because quantum dots have been around for 30 plus years. So the quantum dots themselves, you really can't patent them. You can only patent their application. Right. And you only want to do that if you really have a breakthrough, because obviously, yeah, you can patent things, but patenting costs money and maintaining the patent costs money. So unless you have some sort of technology concept that is really promising, patenting it is usually not a good idea, because it's just going to be a money pit and not likely to yield any kind of benefit. So we've been very conservative, and we haven't really patented much, I guess, because we've had breakthroughs that are good enough to publish in high impact factor academic journals, but as mentioned, we're far from anything that can be considered commercial. So that's why we're not focusing on protecting intellectual property.
Thank you again, and wish you very good luck. Thank you. Good night.
Atasi, Dan, please ask a question.
Thanks, Professor, for the nice presentation. I am also curious to know about the solar window. So just asking, how much percentage of the solar radiation can be used for the photocurrent generation? Because like some percentage, if it is used for photocurrent generation, whether it will be affecting the visibility of the window or not, like how much it will influence the transparency of the window.
Okay, so that's a very good question. Of course, the more photons we use to generate a photocurrent, the less light will illuminate through the window. In reality, it's only a small fraction of photons that are absorbed by the chromophores and that are then concentrated on the solar cells and that end up emitting, being transformed into electricity, which means that the photocurrent densities are not particularly high. And I did mention, in fact, that the efficiency of these solar cells, they're not quite at their best. These solar cells are the commercial ones, the ones that frame the window. They are typical commercial silicon solar cells. So if they were used directly as solar cells, their efficiency would be 20%, but here it's a small fraction of that. So you're not really going to lose a lot in terms of illumination inside the building. but you're also not going to generate a lot of electrical power. This can still be an interesting concept, again, if you have a very tall and large building, which then has many, many windows. So even though the efficiency and the photocurrent generation is low, when you sum up the contributions of many windows, then you can actually have a decent amount of electrical power that is generated. So that's what the concept is really about. It's not so much the efficiency per se, which is far from being again acceptable for commercialization, but the concept that you're exploiting the fact that a very tall and large building has many windows. That's what comes to aid in this trade-off of losing on efficiency.
Okay, thank you for clarifying. And one question in line with that, I think that aspect has been asked before related to the radiation in the infrared range. So is there any way to tailor the infrared radiation so that later on it can influence the thermal property of the room? Like if somehow we can control the infrared radiation, that sometimes in summer days, this kind of window can control the temperature of the room inside the building. So is there any way to tailor that property?
It's an interesting question. I've never really thought about it. I'd have to think about it if there's a way to do that. I don't see an obvious way to do it, but it is an interesting question. What I've seen some people work on is, part of the radiation will, of course, create some, transform into heat. And so some people say, okay, we can transform this heat using thermoelectric materials. But of course, thermoelectric materials typically have very, very low efficiencies. So this is also not considered very viable. Other ways of controlling the temperature of the room, I don't see a straightforward way of doing it, but I'd have to think about it. So I'd have to get back to you on that. I don't have a ready answer for that question.
Okay, thank you so much. Thank you for your nice talk.
Okay, thanks, Adasi. Are there any other questions for Federico? Okay, if not, let's thank Federico for staying up so late to give us this wonderful morning talk. So please use the applause button or unmute yourself. And
my pleasure. Thanks a lot for listening. Hope to meet you all in person one day when this pandemic is behind us.
Okay, thanks Federico. Thanks again. We really appreciate it. Thank you.
Okay. Have a good one.